Why do all lives ultimately end in death? This is something we all know, but cannot answer. In fact, it's not just life. Even our Earth and the entire universe are constantly on the path from birth to death. This is the fundamental law of the universe. No one can change it. Ever since we began lamenting how short life is, almost everyone has been asking, what is the ultimate fate of the universe? After endless time passes, will life still exist? These questions cannot be answered in just one or two sentences. Today, I will start from humanity's first understanding of the universe, traveling through endless galaxies and time, all the way to the final outcome of the universe. After watching this short 1-hour video, you may truly understand what the ultimate fate of the universe is, what it really is. We all know the entire universe is not static. Never has been, but for most of human history, we did believe the universe was static. Looking up at the night sky, the stars seem motionless, night after night, year after year. Constellations remain unchanged. The moon glides steadily. Planets slightly deviate from their paths, but always return. In the eyes of the ancients, all of this was eternal, static, like a great cosmic painting, hanging above the world. So, based on this stillness, we built our understanding of the universe. We believed Earth must be the center, solid and unmoving, everything else the sun, stars, and sky must revolve around us. A perfect celestial dance, driven by something divine, yet endlessly repeating. For centuries, this view persisted, not because people lacked imagination, but because it worked. It matched what the eye saw, made the seasons meaningful, explained the alignment of day and night, gave us comfort, gave us a firm world beneath our feet and an orderly sky around us. Then the illusion shattered. First, Copernicus dared to propose that Earth might not be the center at all. Then Galileo observed the sky with a telescope, seeing satellites orbiting Jupiter, proving not all objects revolve around us. Next came Kepler, who studied planetary orbits and discovered planets do not move in perfect circles, but in ellipses, guided by an invisible force, following precise mathematical laws. Gradually, the silence vanished. Today we know the truth is far stranger than anyone imagined. Space is not silent and fixed. It is everywhere, constantly moving. Not just planets and stars, but galaxies, clusters, and superclusters. Even the fabric of space itself is shifting, stretching in all directions. Yet we still feel motionless. The ground doesn't shake. Starlight doesn't streak past us. The universe feels calm, but this calm is just an illusion of scale, a mirage. Because the truth is, even now, at this very moment, we are spinning on a planet, orbiting a star, racing through a galaxy, while being pulled by a force we cannot even see. The image of a static universe is gone forever. We have entered a story of hidden motion. We are finally beginning to understand what this motion means. For thousands of years, the dominant view of the universe placed Earth at the absolute center. After all, that's what people knew. By day, they saw clouds drifting overhead, the sun shining brightly above, and at night, the moon and stars spreading out like a vast cosmic canvas. Every celestial body seemed to move, and they believed they were at the center of it all. From China's Tianjin to the Mayas' cosmic view, this idea was widespread in the ancient world. But in the Greek world, this idea became not just accepted mythology, but a technical cosmological model. And the man who did this was Claudius Ptolemy. Around the 2nd century AD, Ptolemy lived in Alexandria during the height of Roman Egypt. He was a scholar, mathematician, and, most importantly, an astronomer. He wanted to understand the sky, not just philosophically, but numerically. He inherited Babylonian star catalogs, Egyptian astronomy, and the rich tradition of Greek geometry. But what he did with this knowledge was extraordinary. He compiled, organized, and refined it into a systematic model of the universe. And he wrote a monumental work called the Almagest. This work was profoundly influential. becoming the authoritative guide to the universe for over 1,000 years. In Ptolemy's model, Earth sat at the center of the universe, motionless. Everything else revolved around it, in concentric spheres. The Moon, Mercury, Venus, the Sun, Mars, Jupiter, Saturn, and finally the sphere of the fixed stars. Beyond that, humans knew nothing. The entire universe was a set of giant nested spheres, perfectly ordered. Earth was the center of all celestial motion. Each body was embedded in a transparent crystal sphere, rotating smoothly around us. The stars were fixed on the outermost shell, spinning once a day to create day and night. This wasn't just guesswork. Ptolemy used observations to make his model mathematically functional. He believed celestial bodies must move in perfect circles, because the circle was the most perfect shape in Greek philosophy. But this created a problem as people tracked planets over time, especially Mars, Jupiter, and Saturn. They noticed strange behavior. Sometimes planets would slow down, stop, even move backward in the sky before resuming their forward path. If all planets moved in simple circles around Earth, this retrograde motion made no sense. To solve this, Ptolemy introduced epicycles, small circular paths each planet traveled on, while the smaller circle itself moved along a larger circle called the deferent around Earth. So a planet didn't just orbit Earth, it orbited a point that itself orbited Earth. This looping motion could reproduce the backward step seen in the sky. But even that wasn't enough. Mathematical predictions didn't perfectly match astronomers' observations. So, Ptolemy introduced another adjustment, the equant. This was a point slightly offset from Earth's center. He claimed, if planetary motion was measured from this offset point, the motion appeared uniform, not from the true center, but from this displaced position. The model was refined, polished, and preserved over centuries. It shaped calendars, timekeeping, astrology, and religious worldviews. It served empires and guided scholars. It explained the skies for over 1,000 years. But no matter how complex, it couldn't hide the truth forever. Observers began asking sharp questions. Some started seeking simpler explanations. One name stands out, a name that still echoes with revolution. It all began in 1543, with the publication of a book that shook the foundations of astronomy. The book was called Asterisk on the Revolutions of the Heavenly Spheres Asterisk. The author was not a famous scientist or thinker. He was a priest. His name was Nicolaus Copernicus. This may sound strange today, but it made sense at the time. The church was the center of intellectual life in Europe. If you wanted to study mathematics, astronomy, or philosophy, the church was where you went. Monasteries and cathedrals were the libraries and laboratories of the day. Copernicus was born in what is now Poland, studied law and medicine, dabbled in economics, and was fluent in Greek and Latin. But what he truly loved was the sky. For years, he quietly gathered observations, made calculations, and wrote down ideas forming in his mind. Ideas that contradicted everything he had been taught. His ideas challenged the entire system people believed in. So he kept his views largely private. For decades, he hesitated, knowing the risks were not just scientific criticism, but fierce religious and political opposition. At the end of his life, he reluctantly published his ideas. In the book, he outlined a model of the universe, with the sun, not Earth, at the center. He said Earth, like Mars and Jupiter, was a planet, orbiting the sun once a year. But he didn't stop there. Based on his observations, Copernicus proposed 3 different motions for Earth. First, Earth rotates on its axis once every 24 hours. This daily spin makes the stars appear to rise and set in the sky. Second, Earth orbits the sun once a year. This annual revolution explains changes in planetary positions and the seasons. Third, as Earth travels in its orbit, it slightly wobbles, tracing a small circle, what we now link to Earth's axial tilt, and the precession of the equinoxes. These ideas were not mere guesses. Copernicus spent decades developing complex geometric models and astronomical tables. To calculate the relative distances of planets from the Sun, he ordered them by how fast they moved across the sky. The closer a planet was to the Sun, the faster its orbital speed. This matched perfectly with what he saw. But while Copernicus's model was conceptually sound, it didn't improve accuracy. This was because he still assumed, like Ptolemy, that planets moved in perfect circles. This made his predictions about as accurate as the old system, and in some cases, worse. Then came the telescope. It wasn't invented by a scientist. In fact, it started as a novelty in the Netherlands, just a few lenses put together by an eyeglass maker. But when word of this strange device reached Italy, one man saw more than a curiosity: Galileo Galilei. He didn't invent the telescope, but he turned it into a scientific instrument. In 1610, Galileo pointed it at the sky. What he saw would overturn the old order. First, he observed the moon through his telescope. It was not the perfect, smooth, divine sphere the ancients thought. There were craters, mountains, and shadows. It looked like Earth. Then he looked at Jupiter and discovered four small points of light moving around it. These were moons orbiting Jupiter: 306, 011 to 18,333, 0 hours 11 minutes and 20 seconds, 366, orbiting this planet. This was a major discovery, because the geocentric model claimed everything had to orbit Earth. But Jupiter, with its own orbital system, stole the spotlight. Then he turned to Venus and observed. Venus, like the moon, went through different phases. Sometimes it looked full, sometimes just a thin crescent. This only made sense if Venus orbited the Sun, not Earth. If it orbited Earth, you'd only ever see one phase. But if it orbited the Sun, and we were moving to, then the geometry worked. That tiny glowing dot proved Copernicus right. But Galileo wasn't the one who finally cracked the math. That fell to someone else, someone who didn't even believe Copernicus at first: Johannes Kepler, a German mathematician and astronomer with deep religious faith, intense curiosity, and extreme precision. When he became assistant to the last great naked-eye astronomer, Tycho Brahe, he got a major breakthrough. Brahe, a Danish nobleman, had spent decades collecting the most accurate planetary motion measurements yet, all without a telescope. He built giant instruments on his island observatory and charted planetary positions with unbelievable precision. Brahe didn't buy Copernicus's model. He had his own hybrid theory. Planets orbit the Sun, and the Sun orbits Earth. He tried to bridge the gap, but when he died in 1601, he left all his data to Kepler. Kepler dove in. He spent years trying to fit Copernicus's system to Brahe's data, especially Mars's data. And Mars was tricky. It wouldn't move in a simple circle. It sped up. It slowed down. It looped across the sky. It just wouldn't behave. For years Kepler tried to force the data into circular orbits. Everyone thought circles were divine. Perfect heavens had to move in cycles. But Mars didn't care about philosophy. So, Kepler eventually stopped forcing the math. He let the data speak, and what it said changed everything. Kepler discovered planets don't move in perfect circles at all. They move in ellipses. This was his first law. All planets travel in elliptical orbits around the Sun, with the Sun at one focus of the ellipse. That means planetary orbits aren't perfect circles. They're elongated ovals. Kepler also noticed something else. Planets don't move at constant speeds. When they're closer to the Sun, they sweep through space faster. When they're farther away, they sweep through space slower. This was his second law. The line connecting a planet to the Sun sweeps out equal areas in equal intervals of time. In other words, as a planet travels its elliptical path, whether near or far from the Sun, the area it sweeps in a month is always the same. This explained the planets especially Mars's weird speeds. Then came the third law, which tied the whole system together, also called the harmonic law. Kepler found the square of a planet's orbital period is proportional to the cube of its semi-major axis. Simply put, the farther a planet is from the Sun, the longer it takes to complete one orbit. And this relationship is predictable. Galileo's telescope and Kepler's equations together produced something extraordinary. One gave people a view of a new universe. The other gave them the math to prove it. Copernicus started the revolution. Galileo fanned the flames. Kepler finally built a framework that held it together. Once the door was open, it didn't take long for someone to walk through and push it further. The next generation would turn to the next question. Why do planets move? What force keeps them in orbit? Why don't they fly off into space or fall into the sun? This is where the famous falling apple comes in. Newton named this invisible force gravity. He realized the force that pulls an apple from a tree also keeps the moon in orbit, makes Earth orbit the sun, and governs planetary motion. He expressed it as the law of universal gravitation. According to him, every object with mass pulls on every other object. The more mass, the stronger the pull, the farther apart, the weaker the pull. Thanks to Newton's law of universal gravitation, we know Earth orbits the Sun at about 107,000 kilometers per hour, roughly 30 kilometers per second. Mercury moves faster, about 47 kilometers per second, because it's closer to the Sun and feels stronger gravity. Mars, farther out, moves slower. It all fit. The closer a planet is to the Sun, the faster it has to move to stay in orbit. Newton's math proved it. He linked celestial motion to earthly motion. For the first time in history, we had a set of laws that applied to everything. And just like that, the great cosmic puzzle of planetary motion, why they move, how fast they move was no longer a mystery. It was gravity. But there was something else, something no one saw coming. Because when scientists used better tools and more precise math to map the heavens, they noticed another kind of motion, a bigger, deeper motion. We thought the Sun was still, but it wasn't. It was moving too. But toward what? After the Copernican revolution, the Sun replaced Earth as the center of everything. The universe no longer revolved around us. Now Earth moved, spinning on its axis and orbiting the Sun. The idea felt revolutionary. But once the paradigm shifted, the new model, the heliocentric model, began to settle in. The Sun, once just another object in the sky, now became our fixed point, the anchor of the cosmos, solid and still. For centuries, this view held. But that was about to change. Not with a physicist, not with a philosopher, but with a musician. William Herschel was born in Germany, later moved to England as a composer. But he was obsessed with telescopes. He began building them in his spare time, grinding mirrors, designing optics better than almost anything of his era. When he pointed his telescope at the sky, he wasn't just looking, he was calculating. Herschel became obsessed with structure. If the sky is full of stars, are they randomly scattered or patterned? He decided to find out the hard way. He and his sister Carolyn began a massive survey. He would count stars in narrow strips of sky just a few degrees wide and record how many stars he could see in each direction. Over time, these counts painted a picture. He noticed something strange. Some directions had way more stars than others, and the highest density lined up with the faint band we call the Milky Way. So, he mapped by star count and built what he thought was the shape of the universe. It looked like a flattened, stretched disk, like a grindstone, with the Sun roughly near the center. Today we know he got the scale wrong. He didn't account for interstellar dust, because dust between stars blocks the view of many distant stars. But for the late 18th century, this was extraordinary. He had realized stars weren't infinite. They were part of a structured system, and we were inside it. He called it the Milky Way. But Herschel didn't know this was a galaxy in the modern sense. He thought this system was the entire universe. He had no idea those fuzzy patches, those so-called nebulae, were actually other unimaginably distant galaxies. Even so, what he saw was revolutionary. It showed we weren't the center of everything. Far from it, and that flattened shape meant something. It hinted at structure, motion, direction. If the Milky Way had a shape, then we had a position. If we had a position, then maybe we were moving to. From then on, people started asking a deeper question. Where exactly are we? So how do you know what's moving? And what isn't? Because if everything is moving, how do you know when something is still? That's when we hit a wall. Not a wall of data, but a wall of perspective. Because everything we see is seen from Earth. Our eyes, telescopes, instruments, they're all on this spinning rock. And this rock itself orbits the sun. Just as Herschel suspected, the sun might be moving too. So, how do you figure out what's really moving? And what isn't? This is where reference frames come in. Let's try a simple thought experiment. Imagine you're on a train, drinking coffee, reading a book. From the window, you see another train stop beside you. For a moment, that train seems to slide backward. But wait, are you moving? Or is it? Or are you both moving? The thing is, if you don't look at the ground, you can't tell. That's the trap of your reference frame. From inside the train, everything seems still. Coffee stays in the cup. The book sits quietly on your lap. But to someone on the platform, you're moving at 80 kilometers per hour. So who's right? Well, actually both. Because motion isn't absolute, it's relative. When your only window to the universe is from inside a train, orbiting a star, on a spinning Earth, and that star is moving too. Figuring out the real motion is a puzzle. One man quietly, patiently set out to solve it. Jacobus. Captain never saw himself as a revolutionary. He was quiet, cautious. A man who loved numbers more than noise. But his work with those numbers changed how we understand the cosmos. Captain was born in mid-19th century Holland, when Herschel's star map was already over a century old. The idea we lived in a star system, what we now call the Milky Way, was accepted. But structure, motion, it was still fuzzy. Telescopes were getting better, but astronomers needed more than better tools. They needed a new approach. That's what Captain brought. He started collecting data. Not just light, not just position, but proper motion. How stars drift across the sky. Over time, these are tiny shifts. Often just fractions of an arcsecond per year. But with the right math, and enough time, they tell a story. He gathered observations from observatories around the world. Cape Town, South Africa, Cordoba, Argentina, Sydney, Australia. He compiled thousands of star catalogs bit by bit, measuring their brightness, measuring their positions, watching their drift. Then something strange emerged. Stars weren't drifting randomly. They moved in patterns. Two great streams like cosmic rivers, flowing across the sky. At first these stars looked like they were converging into two giant rotating clusters. But Captain thought harder. What if this had nothing to do with the stars? What if we were the ones moving? Back to the train analogy. Imagine you're walking steadily through a crowded plaza. People seem to stream past you from different directions. But maybe you're the one moving, and everything else only seems to drift because of your reference frame. Captain ran the numbers. He did the calculations, and it all fit. Only if the sun was moving, dragging us along with it. Did the star motion patterns make sense? This motion is called the solar apex. According to Captain's observations, the sun is moving at about 20 kilometers per second toward a point in the constellation Lyra. It's not a sprint, but a steady, silent drift through space. And just like that, the sun lost its claim to stillness. But Captain didn't stop there. He wanted more. If we're moving through the stars, then what are these stars? What kind of system are we in? Using star motion and brightness, Captain began building what he thought was the true shape of our galaxy. He assumed stars were evenly distributed in space, and their brightness dimmed with distance. From this he proposed a model. It looked like a flattened disc-like structure, about 40,000 light-years across. In this structure, what Captain called the universe, the sun sat near the center. This was our first real attempt to map the entire Milky Way. Of course, we now know Captain's universe was too small. He didn't know about interstellar dust, tiny particles floating between stars that absorb and scatter light, especially in the plane of the galaxy. This made distant stars appear dimmer, making them seem closer than they were. So, his model underestimated the galaxy size and shape, but at the time, it was groundbreaking. Then came the turning point. Astronomers grew curious about those faint, fuzzy patches in the sky, the so-called spiral nebulae. Some thought they were part of our Milky Way, but others suspected something more dramatic. They might be entire star systems of their own. That's when Edwin Hubble stepped in. Hubble used the Hooker telescope on Mount Wilson, then the most powerful telescope on Earth, to observe one of the most prominent nebulae, the Andromeda Nebula. In 1923, he found something crucial inside it, a type of star called a Cepheid variable. These stars brighten and dim in a predictable pattern, thanks to Henrietta Leavitt's earlier work. That pattern could be used to calculate a star's true distance. The answer stunned him. Andromeda wasn't just far away, it was far beyond the edge of the Milky Way. In fact, so far, it couldn't possibly be part of our galaxy. This was a massive shift. For centuries, we thought the Milky Way was the entire universe, but now it was just one of many galaxies, an island in a vast cosmic ocean. But here's what really mattered. By studying these other galaxies, we began to see our own galaxy more clearly. You can't see the Milky Way from the outside. We live inside it. It's like trying to map a forest from the roots of a tree. But with Andromeda and other galaxies, we finally had something to compare. We could look at galaxies from the outside and ask questions like, does our galaxy also have a spiral structure? Does it have a central bulge, a flattened disk, or a stellar halo? In the decades that followed, astronomers used this mirror effect, comparing external galaxies to what we observed inside the Milky Way. They mapped gas clouds, star clusters, and stellar populations. They used radio astronomy to peer through dust that blocks visible light. Gradually, a new picture emerged. One of them was Dutch astronomer Jan Eert. He closely studied the motion of stars near the sun. He wasn't just interested in their positions, but in how they moved. His findings were odd. If the Milky Way rotated like a solid wheel, then every star should move at the same angular speed, like spokes on a bicycle wheel. But it didn't. 795, 0 hours 29 minutes and 1 second. 600, 0 hours 29 minutes and 3 seconds to 100. Some stars were lagging behind. These numbers made him realize that the Milky Way is rotating, but the speed is not uniform. It rotates faster near the center and slower at the edges. He deduced the mathematical principles behind it and derived two constants used to describe the way stars move in the vicinity of the Milky Way. These two constants are now known as the Oort constants. For the first time, they truly describe the differential rotation of the Milky Way. Based on this, he calculated that our Sun is about 30,000 light-years from the center of the Milky Way and is moving at an astonishing speed of over 200 kilometers per second. That's enough to circle the Earth 7 times in 1 minute. At this speed, the Sun takes about 225 million years to orbit the center of the Milky Way once. That's 1 galactic year. And the Sun is not fighting alone. Every star you see in the sky is doing the same thing. Like bees buzzing around a hive, they orbit the center of the Milky Way. We just don't feel it, because we're all moving together. But if that's the case, what exactly are we orbiting around? To answer this question, astronomers needed better eyes that could see beyond visible light. So they turned to radio waves. Specifically, they began mapping neutral hydrogen atoms emitting faint natural radio signals. This signal has a wavelength of 21 centimeters and can penetrate thick dust clouds that make optical observations nearly impossible. By tracking this signal, astronomers began mapping from the inside the spiral arms of the Milky Way. It's like standing in a forest, trying to draw a map of the woods. But now they had the tools. Then the biggest leap came with the Very Long Baseline Array, or VLBA. The VLBA is not a single telescope. It is a system of 10 radio antennas, spread thousands of kilometers apart. Imagine placing 2 telescopes at opposite ends of the Earth, one in Hawaii, the other in the Virgin Islands. Now imagine them working in perfect synchronization. They act like a giant antenna the size of an entire continent. That's essentially what the VLBA does. It connects 10 observatories scattered across the Western Hemisphere to form a super instrument capable of resolving extremely tiny movements in the sky. What we call SMILE refers to micro-arcsecond movements. It's like distinguishing a coin on the moon from Earth. Astronomers use this system to track cosmic beacons called masers. These are not visible lasers, but radio signals naturally emitted by gas clouds around newborn stars. These act like lighthouses in space, bright, compact, and perfect for tracking. Since they are locked to specific regions in our galaxy, they help us precisely locate positions and velocities. After years of observation, astronomers saw these objects slowly moving across the sky. They measured changes in their positions, that is, proper motion, and how their light shifted red or blue, that is, radial velocity, whether they were approaching or receding from us. Combining these, you get a complete three-dimensional picture of motion, not just left-right, not just forward-backward, but the full trajectory of stars in the Milky Way. And what did that dance reveal? It showed that stars orbit the center of the Milky Way, but not in perfect circles. Their motion forms spirals, twisted and stretched under gravity and the galaxy's own structure. Some arms lead, others lag. Star clusters swing, gas clouds shear under tidal forces. But at the heart of it all, something strange exists. At the core of all this, there is something odd. As these arms and other stars get closer to the center of the Milky Way, something becomes obvious. Their speeds increase dramatically. Objects near the center are orbiting at astonishing speeds. But the key is, there isn't enough visible matter to explain that gravity. There are stars, yes, dust, gas, but far from enough to hold matter together. At those speeds, something invisible is holding the Milky Way together. All this motion, all these calculations, all these precise measurements point to the same place. A dense, concentrated radiation point near Sagittarius. This point is called Sagittarius A*. It doesn't look like visible light, just a haze of dust and stars. But at radio wavelengths, it glows. VLBA observations focused on it and found it to be a relatively stationary object, with everything else orbiting around it. Its mass is over 4 million times that of the Sun, and smaller than the orbit of Mercury. The only thing in physics that fits these numbers, so small, so dense, so massive, is a black hole, a supermassive black hole. It anchors the Milky Way. It sits quietly at the center, barely flickering, while every star in the Milky Way, every planet, every gas cloud orbits around it. Yet we are not standing still. Because stars aren't just orbiting the center. The entire Milky Way is warping, twisting, wobbling. The Orion arm we live in is gently rising and falling like a surfer on a wave across the galactic plane. But even the Milky Way is not standing still. Our entire galaxy is in motion, drifting, pulled by invisible forces. A car speeds toward you, engine roaring. As it zooms past, its pitch rises as it approaches and drops as it recedes. This is the Doppler effect. It happens when an object producing waves, like sound waves, moves toward or away from you. As it approaches, the waves bunch up. As it recedes, the waves stretch out. The same happens with light. If a star or galaxy is moving toward us, its light waves are compressed, shifting slightly toward the blue end of the spectrum. We call this blue shift. If it's moving away, the light waves stretch, shifting toward the red end. This is redshift. In the 1910s and 1920s, scientists began using this method to measure the motion of stars and galaxies. One of them was Edwin Hubble. His discovery was shocking. Most of the galaxies he observed were not standing still. They were moving away from us. The farther a galaxy was, the faster it was receding. Some galaxies were moving away at hundreds of kilometers per second. Others at thousands of kilometers per second. Hubble plotted this pattern, and with each new galaxy, the pattern held. The farther away, the faster the speed. The universe itself is expanding. Galaxies are just along for the ride. This was one of the greatest discoveries in scientific history. It meant the universe had a beginning. It meant everything we see today was once closed together. It even laid the foundation for the Big Bang Theory. But not all galaxies are moving away from us. One galaxy stood out. It was a familiar neighbor. The giant spiral galaxy, the Andromeda Galaxy. In 1912, an American astronomer named Vesto Slipher pointed a telescope at Andromeda and measured its spectrum. People were just beginning to understand how redshift and blueshift worked in galaxies, and what Slipher observed went against all their expectations. Like most galaxies, Andromeda showed redshift, but also blueshift. This meant it was coming toward us, but at the time, they could only say it was one direction, not the full picture. Fast forward 100 years. Technology had advanced greatly. We had space telescopes, supercomputers, and radio antenna networks around the world. Astronomers used data from NASA's Hubble Space Telescope combined with the Gaia mission and precise VLBA measurements by tracking Andromeda's actual motion over years. Not just light shifts, but its sideways motion. They pieced together its full 3D trajectory. Their findings confirmed that Andromeda is not just drifting nearby. It won't slingshot past us. It is locked in. It is on a direct collision course with the Milky Way. And we are heading toward it. Andromeda is not just coming toward us. Both of us are rushing toward each other through the void of interstellar space. Currently, Andromeda is moving toward us at about 110 kilometers per second. The Milky Way is not standing still either. If we account for the motion of our entire local group, we are approaching Andromeda at nearly 300 kilometers per second. This means when we add both galaxies together, the distance between us is shrinking at about 500 kilometers per second. Yet the universe is vast, incredibly vast. Andromeda is about 2.5 million light years away, roughly 24 quadrillion kilometers. That's a number so large it feels unreal. At this speed, even with both galaxies rushing toward each other, the approach isn't fast enough to happen in the short term, so not tomorrow. Not next year, but in about 4 to 5 billion years. These two largest galaxies will finally meet. Now you might imagine a galactic collision. Stars smashing into each other. Chaos. Fire everywhere, but that's not how it works. Galaxies are mostly empty space. The stars inside are incredibly far apart. On average, in our Milky Way, stars are 4 to 5 light-years apart, nearly 40 quadrillion kilometers. Even in denser core regions, stars are typically a light-year apart, or more. For example, if a star were the size of a ping-pong ball, its nearest neighbor would be hundreds of kilometers away. So even if the galaxies collide head-on, most stars will pass like ships in the night, close, but never touching. However, galaxies are not completely calm, especially in crowded central regions. And a few stars, especially on the edges, may be flung out entirely, ejected like cosmic flotsam into intergalactic space. But the real drama happens under gravity. This invisible force stretches and twists the galaxies. It flings out long tidal tails, pulling streams of stars from their homes. It tears apart spiral arms. It draws the galaxies closer and closer, until they finally merge into one larger, more chaotic system. But the full collision doesn't happen all at once. The first pass is quick, a close encounter that triggers chaos. But the merger itself is slow. It takes about 1 to 2 billion years to fully settle down. This isn't a crash. It's a slow, graceful gravitational ballet. When the dance ends, something new is born, a giant elliptical galaxy. Astronomers have already named it Milkometa. It won't look like a spiral anymore. It will be puffier, rounder, a giant glowing ball of stars, gas, and dust. Assuming our sun is still alive, it will likely enter a new orbit. Not where it is now, not in a neat spiral arm. It may follow a more elliptical, less stable path, drifting farther from the center. But the collision with Andromeda is not the whole story. It is not our galaxy's only trajectory, because the Milky Way, Andromeda, and hundreds of other nearby galaxies are not just being pulled toward each other, they are being pulled toward something larger, something stranger. But to understand our future direction, we must zoom out. First past our solar system, then past the Milky Way, even past the group of galaxies we belong to, because galaxies do not float in isolation, they cluster together, following gravity like water flowing downhill. Let's start small. Our Milky Way is part of a galaxy group of about 80 galaxies, called the Local Group. It spans about 10 million light-years. The Milky Way and Andromeda are the two largest galaxies in this group. Each is surrounded by smaller satellite galaxies like the Large and Small Magellanic Clouds, or M32 and M110, orbiting Andromeda. But this group is just a small part of a larger galaxy cluster. Galaxy clusters are collections of galaxy groups bound by gravity. The Local Group is just a minor member of the Virgo cluster. The Virgo cluster is a larger collection with over 1,000 galaxies. The Virgo cluster is about 65 million light-years away, and its gravity is pulling us. We're not just floating beside it. Our entire Local Group is moving toward the center of the Virgo cluster at about 600 kilometers per second. So galaxy groups are inside clusters. But even clusters are not the end of the story. Clusters of clusters form superclusters, the largest known structures in the observable universe. They can span hundreds of millions of light-years and contain tens of thousands of galaxies. Our cluster is called the Laniakea Supercluster. The word means immense heaven in Hawaiian, and it fits. The Laniakea Supercluster is enormous, spanning over 500 million light-years, and containing about 100,000 galaxies, including the Virgo cluster, the Centaurus cluster, the Hydra cluster, the Pavo-Indus supercluster, and the Southern supercluster. They are interconnected, forming a cosmic web of flows. So how do we know all this? How do scientists determine where galaxies are moving? How fast and in what direction? It all comes down to motion. Over the past few decades, astronomers have not just observed where galaxies are, they've mapped how they move. To do this, they needed more than just redshift and blueshift. They needed peculiar velocities, the actual motion of galaxies, relative to the overall expansion of the universe. This is not easy. You can't just take a snapshot and know how fast a galaxy is moving sideways through space. You have to combine multiple techniques. One of the most important is the Tully-Fisher relation. Astronomers use it to compare the brightness of spiral galaxies with their rotation speed. If you know a galaxy's intrinsic brightness and compare it to its observed brightness, you can estimate its distance. Once you know the distance and redshift, you can determine its motion relative to Hubble's overall expansion. Faster or slower, that difference is its peculiar velocity. This motion is caused by local gravity, not just cosmic expansion. That's where the real insight comes from. The Cosmic Flows Project, Cosmic Flows 2, and later the more detailed Cosmic Flows 3, were massive efforts to collect motion and distance data for thousands of galaxies using the Tully-Fisher relation, surface brightness fluctuations, and even supernova data. Scientists built 3D velocity maps of our cosmic neighborhood, revealing not just where galaxies are, but how they move. Galaxies are flowing. Their discovery was shocking. Galaxies are not just expanding outward like dots on a balloon. They are also flowing toward a specific direction, toward something we can't directly see, something massive. And this flow is not chaotic. It is coherent, organized. This motion points beyond Centaurus and Norma to a mysterious region of space, obscured by the thick dust belt of the Milky Way. The real mystery begins here. What are we being pulled toward? Astronomers noticed this strange flow as early as the 1970s. Galaxies, including ours, are not just drifting with the expanding universe, they are moving sideways at hundreds of kilometers per second, all in the same direction. But when telescopes looked in that direction, they hit a wall, the zone of avoidance, a region of the sky packed with stars, gas, and dust from our own galaxy, blocking our view of anything behind it. Despite this, the motion was undeniable. Scientists called the source of this gravity the Great Attractor, not because they could see it, but because they could feel its pull. Entire clusters of galaxies are tilting toward it, and we are caught in the same gravitational current. Astronomers used X-ray telescopes and infrared surveys to piece together the picture bit by bit. They found massive concentrations of mass hidden behind the plane of the Milky Way. This is not a single object. It's a region of space filled with galaxy clusters. The largest of these is the Norma cluster, about 220 million light-years away. And this cluster is not isolated. It is part of an even larger structure. This region, this attractor, turns out to be located in an even larger cluster of galaxies, 1303. 047 to 58,666 as 0 hours 48 minutes and 1 second, 500, and this galaxy cluster is not isolated. This region, this attractor, turns out to be located near the edge of a much larger galaxy cluster, the Shapley supercluster. It is one of the largest known superclusters in our local universe. This is what is pulling us. The gravity of the Shapley supercluster is so strong that it bends the paths of galaxies across vast regions of the universe, even though we cannot directly see it. Invisible light, its mass, is dragging our entire supercluster toward it. We are moving in its direction at about 600 kilometers per second. Now things get tricky. This is not a clear, definite destination. We are not falling into the Great Attractor like a stone into a hole. We are caught in a cosmic tug-of-war. Gravity does not just pull, it also warps space. So while the Great Attractor pulls us toward it, other forces in the universe are also shaping our path. And one of the strangest forces shaping this path is not a force at all, it is the dipole repeller. Let us slow down. The dipole repeller is not an object. It is not a galaxy. It is not even something you can see. It is an unusually empty region of space, a cosmic void. With almost no matter, there are no massive galaxy clusters, no significant gravity. But this emptiness matters, because while massive objects pull galaxies toward them, giant voids do the opposite. They make it easier for galaxies to drift away. You are floating in a river. On one side is a waterfall pulling you in. That is the great attractor. On the other side is calm water. No current, no force, that is the dipole repeller. You are not pushed by it. You are simply not held back, so the waterfall wins. That is the kind of gravitational flow our galaxy is caught in. Astronomers in 2017 began to see this more clearly when they used Cosmic Flow's 3D data and 3D motion maps of over 18,000 galaxies. What they saw was not just a pull in one direction, it was a dipole pattern. Galaxies like ours are flowing away from the repeller and toward the great attractor. But this is not the end of cosmic motion. When you zoom out far enough through clusters, supercluster filaments, and voids, a new pattern begins to emerge. A deeper flow, one that spans the entire observable universe. All the grand structures of the cosmic web are not static, they are drifting somewhere. So far, we have been following Earth's rotation and revolution. We saw through the Milky Way. Then we zoomed out and found that even the Milky Way itself is moving, part of a vast cosmic flow, towards something we cannot even see. Imagine we are on a moving rock, and that rock is part of a moving system within a moving galaxy. That is already mind-blowing, but now it is time to go bigger. Now it is time to ask the final question. Where is everything in the universe headed? Not just Earth, not just our galaxy, but everything. What is the ultimate fate of the universe? To answer this, we have to talk about something strange. Something that does not shine or glow. Something pulling the strings behind the scenes. When we discovered something very strange, it shook science to its core. Ironically, the story begins with the end of the universe, or at least attempts to predict the end of the universe. In the 1990s, two teams of scientists, one led by Saul Perlmutter, the other by Brian Schmidt and Adam Rees, were studying exploding stars, known as Type Ia supernovae. These explosions are extremely bright and explode in roughly the same way, making them perfect cosmic mile markers. If you know how bright a supernova should be, and it appears dimmer than expected, then you know it is farther away. The goal was to measure the rate at which the universe is slowing down. You heard that right, slowing down, because the assumption at the time was that after the Big Bang, the universe began expanding, and gravity was slowly pulling everything back. But the data showed something else. When they measured these supernovae, they found something wrong. These galaxies were not just far away, they were too far. The redshift of their light was greater than expected. This meant the galaxies were not just moving away, they were accelerating. The universe was not slowing down, it was speeding up. Now imagine you are a physicist and suddenly realize every assumption about the future of the universe was wrong. That is what happened in 1998. But the teams did not ignore it. They double-checked everything. But the result was always the same. Some invisible, powerful thing was tearing the universe apart faster and faster. They called it dark energy. We do not know what dark energy is made of. We do not even know if it is a thing at all. But we do know it is real, and that it dominates the universe. Of all the energy and matter that exists, about 70% is dark energy. To understand how strange this is, think about everything you have ever seen, touched, tasted, or heard in your life. All the stars, all the planets, every atom makes up less than 5% of the universe. Another 25% is dark matter, which uses gravity to hold galaxies together. The rest, the largest piece of the universe, is the silent force tearing the universe apart. So what could it be? This is where things get tricky. Physicists have some guesses. The most straightforward idea is that dark energy is simply the vacuum energy of space. Even though space looks empty, it is not really empty. It is filled with quantum fluctuations, tiny bursts of energy flickering in of existence, appearing and disappearing. Now here is the interesting part. When you do the math, quantum theory actually predicts that empty space should have energy. But that is not the craziest part. The crazy part is how the predicted vacuum energy should be 10 to the 120th power times stronger than what we actually observe. In other words, quantum theory's estimate of the true value of vacuum energy is off by a huge margin. This is the largest mismatch between theory and observation in the history of physics. It is like trying to weigh a feather, and your calculator says it weighs more than the entire Earth. Yes, something is wrong. That is the problem. This vacuum energy, the energy of empty space, is not just sitting there. According to Einstein's equations, energy and pressure shape the structure of space-time. This means that if space really has energy, then it will affect how the universe expands. That is where dark energy comes in. We observe that the universe is expanding faster and faster. Whatever is causing this acceleration must be built into the very fabric of space itself. This led scientists to think that vacuum energy might be the factor driving this expansion. Maybe dark energy is just the energy of empty space. But if that is true, then quantum theory's predictions should match what we observe. But they absolutely do not. 1519. 056 to 11,566, 056 to 13,466. This isn't just a little off, or we're missing a huge piece of the puzzle. Imagine space as a giant raisin. Bread. Galaxies are like raisins baked into the dough. As the bread bakes, it expands. The raisins move away from each other. That's the universe expanding. But now imagine, halfway through baking, something raises the temperature. The dough doesn't just rise, it expands faster and faster. That extra push is dark energy. The bigger the bread gets, the faster it expands. Because dark energy isn't simply distributed into space. It is space itself. The more space there is, the more dark energy there is. It doesn't get diluted. It doesn't run out. That's what makes it so terrifying. Now here we stand, watching the universe expand ever faster. And the engine behind this runaway growth is dark energy. This invisible, intangible force doesn't cluster, doesn't slow down, and the more space there is, the stronger it gets. That's already strange enough. But now comes the truly unsettling part, where this is taking us. Assuming dark energy keeps doing what it's doing, keeps pushing, keeps stretching space, what happens in the long run? This leads to one of the most terrifying predictions in all of cosmology. It's called the Big Rip. Here's how it works. In our current universe, gravity is still strong enough to hold things together. Galaxies won't be torn apart. Stars still orbit their centers. Planets stay attached to their stars. Even though space is expanding, the forces inside galaxies are still stronger than the pull from expanding space between neighboring galaxies. But dark energy doesn't follow those rules. It grows relentlessly. In some models, it doesn't just keep accelerating the universe's expansion. It accelerates the acceleration. Imagine you're in a car going downhill, gaining speed, and then the slope gets steeper and steeper. That's the Big Rip scenario. At first, you wouldn't notice anything. Galaxy clusters slowly separate. The space between the Milky Way and Andromeda grows too fast for them to ever collide. But it doesn't stop there. Eventually, galaxies themselves start to stretch. Not just pulled apart, but torn from the inside. Gravity weakens. Then, the bonds holding stars in place snap. Then, star systems like our solar system fall apart. Planets break out of orbit, satellites vanish into the void. The tidal forces that keep everything balanced disappear, and it keeps going. As the acceleration intensifies, even Earth itself isn't safe. The expansion force becomes so powerful that it overwhelms the electromagnetic forces binding molecules together. The crust will crack. Atoms will split. As space itself stretches, Beyond the range any particle can survive. Even the building blocks of matter, protons, may be torn apart. In the final moments before the Big Rip, the universe becomes a storm of fragments. In 20 billion years, there will be no more galaxies, stars, or atoms, only pure, unbound energy, flickering in an ocean of nothingness. That timeline is just a guess based on one model. It could happen much sooner, or it might never happen. Because it all depends on how dark energy behaves, and we still don't fully understand it. But not all theories end in failure. Some take the opposite approach. There's another idea. It starts with a question. What if the universe's expansion doesn't go on forever? What if, at some point, gravity fights back? You see, in the early universe, everything was hot and dense, space was expanding, but gravity was pulling back, trying to slow everything down. This tug-of-war has been going on from the beginning. For a long time, scientists thought gravity might eventually win. That's the Big Crunch theory. In this version of the story, expansion is temporary. One day dark energy might weaken. Or maybe it wasn't permanent to begin with. If that happens, gravity could take over again. At first, it would slowly start pulling everything back together. Galaxies that were drifting apart would start moving toward each other. Structures would reverse. The vast web of the cosmos would contract. Billions of years later, the universe would shrink. As all matter is squeezed into an ever tighter volume, temperatures would rise. The night sky would grow brighter. Not from the birth of starlight, but because in a shrinking universe, old stars collide with each other. Space-time fabric would curve inward like a clenched fist. In the final seconds, the entire universe would become a single hot, dense point. Then it might end. Or it might begin again. The Big Crunch has a poetic symmetry. The idea that the universe ends where it began. The Big Bang, just one phase in a cycle of expansion and collapse. Bang, then crunch, forever cycling. Bang, then crunch, forever cycling. But this picture has a problem. The math doesn't quite add up. So far, everything we've observed, galaxy redshifts, the cosmic microwave background radiation, tells us the universe isn't slowing down. It's speeding up. That means gravity isn't winning. At least not yet. So, unless dark energy changes dramatically in the future, the Big Crunch seems unlikely. But here's the thing. We don't fully understand yet what dark energy really is. It's a placeholder for something we can measure, but can't explain. We know it causes the universe to expand faster and faster, but we don't know why. If someone could figure out the true nature of dark energy, it wouldn't just be a breakthrough. It would be Nobel Prize material. But until then, we can only watch what's in front of us. Still, there's one more possibility, one more future. It's not as dramatic as ripping or crunching. It doesn't explode or collapse. It just keeps going. This might be the most haunting ending of all. It's the Big Freeze, a universe that doesn't die in violence, but fades away in silence. Here's how it goes. We've talked about dark energy, how it pushes the universe to expand faster and faster. We've also discussed, unless something major changes, this expansion will continue. Now imagine, the universe follows this path. Galaxies drift farther and farther apart, but the speed never slows. The stars within them are aging, burning through their fuel one by one. This idea of cold, endless fading isn't just poetic. It's backed by some of the best data we have. Andrei Lind is a Russian-American physicist, famous for his work on inflation theory. He contributed to models that support this outcome. According to measurements from tools like the Planck satellite and large sky surveys like DASI Dark Energy Spectroscopic Instrument, the expansion rate is consistent with a cosmological constant. This means dark energy may stay constant over time, not increasing or decreasing, just humming along, gently stretching space. If that's true, then the Big Freeze isn't just a possibility. It's the most likely fate of our universe. Now let's zoom out and trace the future step by step. We're in the present era. Galaxies are still relatively close. Stars are being born in places like the Orion Nebula. Planets orbit their stars. Life breathes. Black holes devour the cosmos. The web still glows with energy, but time marches on. Give it 100 billion years. By then, the observable universe we can see will have shrunk dramatically, not because the universe itself is smaller, but because the space between us and distant galaxies is expanding faster than light can cross it. Those galaxies will fall beyond our cosmic horizon. We'll never see them again. They'll still exist, but forever out of reach. Like ships sailing off the edge of an endless ocean. After enough time, even the nearest galaxies will vanish from view. Eventually, the Milky Way and Andromeda, having long since merged into one giant elliptical galaxy, will become an island floating in a dark, silent ocean. The journey of stars doesn't last forever. Star formation requires gas, mainly hydrogen. But that gas won't last forever. When stars go supernova or shed their outer layers, they recycle matter back into the galaxy. But over time, the recycling slows. The fuel runs out. It's estimated that, in about 1 trillion years, star formation across the universe will completely stop. The remaining stars will slowly burn out their fuel. Red dwarfs, the smallest, coldest, dimmest stars, can live for trillions of years. They'll be the last flickers of light in an otherwise pitch-black sky. But even they will eventually burn out. After that, only remnants remain: white dwarfs, neutron stars, black holes. Then we enter what's called the degenerate era, an era with no new stars, no starlight. The universe is made of cold, collapsed objects, white dwarfs and black holes, still hungrily devouring whatever they can. Time keeps marching. Over the next 1,040 years, that's a 1 followed by 40 zeros, these stellar remnants will decay. White dwarfs cool into black dwarfs. Neutron stars may stay stable for a long time, but black holes have their own clocks. According to Stephen Hawking, black holes aren't eternal. They slowly evaporate through a quantum effect called Hawking radiation. Over time, they lose mass, very slowly. A black hole the mass of our sun would take about 1,067 years to fully evaporate. Let's put that number in perspective. Our entire universe is only about 13.8 billion years old now. Compared to the timescales we're talking about, that's nothing. In the Big Freeze, time stretches far beyond anything we can truly imagine. Eventually, every black hole evaporates. They disappear one by one in tiny flashes of radiation. No more stars, no more starlight, no more light. The universe becomes a sea of particles, electrons, positrons, maybe some decaying protons, drifting alone in a cold, expanding ocean of space. Temperatures drop to absolute zero, not because there's no heat, but because there's nothing left to produce heat. No fusion, no gravity pulling things together, just particles scattered across an ever-expanding void. Even protons may not survive. If proton decay is proven real, then all matter itself could disintegrate. Some models predict this could happen in about 1,036 years. Then what's left? Nothing but a faint glow of radiation. The background light of a universe that once teemed with stars, galaxies, and life. The universe keeps expanding until everything is too far apart to interact. Temperatures too low to change anything. Even the concept of location becomes meaningless. The laws that gave birth to everything still exist, inscribed in a cold, meaningless void. But now there's no one to read them. This will be the ultimate fate of our universe.